In a quiet garden, an apple detaches from its branch. Time itself seems to slow, the world holding its breath as the fruit hangs suspended, a single moment stretched into an eternity.
How?
What pulls it down? This simple, everyday event sparked one of the most profound questions in human history. It was a question that would lead one man, Isaac Newton, to unravel the very fabric of the cosmos. Before Newton, the heavens and the earth were seen as two separate realms, governed by entirely different rules. The celestial bodies, the sun, the moon, the planets moved in perfect divine circles, while objects on earth simply fell. It was a comfortable, accepted truth. But for Newton, this separation didn't make sense. He was a restless thinker, driven by an insatiable curiosity and an extraordinary gift for mathematics. He saw the world not as a collection of disconnected events, but as an intricate, interconnected machine, a grand puzzle waiting to be solved. The falling apple wasn't the discovery itself, but the catalyst. It was the spark that ignited a revolutionary idea. What if the force pulling the apple to the ground was the very same force that held the moon in its orbit around the Earth? It was a radical, audacious leap of imagination. To test this theory, Newton would need a new language, a new tool to describe a world in constant motion. And so, he invented one: calculus. With calculus, Newton could finally describe the poetry of motion in the precise language of mathematics. He could calculate the changing speed of a falling object, the curve of a thrown stone, and, he hoped, the majestic arc of the moon. He began to visualize the universe differently. He imagined invisible threads stretching out from every object, a universal web of influence. He pictured the Earth not just pulling on the apple, but on the moon, and the sun pulling on the Earth. And on all the other planets all at the same time. His calculations were painstaking. He had to estimate the distance to the moon, the size of the Earth, and the speed of the moon's orbit. The data available in the 17th century was imprecise, but Newton persisted, refining his work over years. He envisioned a cannonball fired from a mountaintop. Fire it with a little force, and it falls back to Earth. Fire it with more force, and it travels further before falling. But what if you could fire it with just the right amount of force, at just the right speed? Newton realized it wouldn't fly off into space, nor would it fall back down. Instead, it would continuously fall asterisk around asterisk the Earth, entering a state of perpetual orbit. This was the secret of the moon. The moon is constantly falling towards the Earth, but its sideways motion is so great that it continually misses, tracing its elegant path across our night sky. The force pulling the apple and the force holding the moon were one and the same. Called it universal gravitation. This idea was captured in a single, elegant equation: F equals G times M, 1 times M2 over R squared. This is the law of universal gravitation. It states that every particle in the universe attracts every other particle with a force. That force is stronger if the objects are more massive, and it gets weaker as the distance between them increases. It's a law of beautiful simplicity and staggering power. Suddenly, the entire universe, from the smallest grain of sand to the most distant star, was united under a single, understandable principle. The cosmos was no longer a realm of divine mystery, but a predictable, mechanical system. With Newton's law, we could understand the ebb and flow of the tides. It's caused by the gravitational dance between the Earth and the Moon. We could predict the paths of comets as they streak through the solar system. We could even discover new worlds. Decades after Newton, astronomers noticed Uranus was wobbling in its orbit, not moving quite as predicted. Using Newton's law, they calculated that another unseen planet must be pulling on it. They pointed their telescopes to that exact spot in the sky, and there it was, Neptune. A planet discovered not by sight, but by the pure power of mathematics. Newton's gravity can be visualized as a force field, a pervasive influence that warps the space around it. Imagine the sun as a heavy ball placed on a stretched rubber sheet. It creates a deep well, a dip in the fabric of space-time. The planets, like smaller marbles, roll around the edge of this well, their paths dictated by the curve created by the sun's mass. This is gravity, not just a pull, but a shaping of the universe itself. It's the silent architect that gathered dust and gas into stars and planets. It's the cosmic glue that holds galaxies together, preventing them from flying apart. It orchestrates the grand ballet of celestial bodies, a performance on a scale almost too vast to comprehend. Everywhere we look, we see Newton's legacy. It's in the satellites that orbit our planet, providing communication and navigation. It's in the design of spacecraft that journey to other worlds, their trajectories calculated with the same principles Newton pioneered. His discovery didn't just change science, it changed humanity's place in the universe. We were no longer just passive observers of a divine play. We were inhabitants of a physical cosmos, capable of understanding its deepest laws. From a single falling apple, Isaac Newton gave us the keys to the universe. He taught us that the same laws that govern our everyday world also govern the grandest cosmic scales. His work stands as a timeless testament to the power of human curiosity, reason, and the relentless pursuit of knowledge. It reminds us that even the simplest questions can lead to the most extraordinary answers, and that the universe is a book written in the language of mathematics, waiting for us to read. Thank you for joining us on this journey through space and time. If you were fascinated by the story of gravity, make sure to like, subscribe, and follow for more explorations into the wonders of our universe.